Simon. Thank you, everybody. It's an honor to be here virtually, and I look forward to the next hour or so to have a casual discussion about our own work as well as some other colleagues' work in the field of cryogenic electronics. So as you see, my talk title talks about computing at the ultra cold. So there will be an emphasis on the computing aspect, obviously. And when you talk about ultra cold, one of the things that will come to our mind is superconductivity. But turns out that's not the only thing that works at the cryogenic environment or can be used or utilized in cryogenic electronics. However, since this is IEEE CSE, I will be focusing most of this discussion on the superconductivity related stuff. So without further ado, let's get started. This is an overview of my presentation. I'll start with some background and motivation, and then I'll talk about the applications of cryogenic electronics, obviously very briefly. And then I'll move over to discussing specifically some of our works on superconducting logic, and then move over to superconducting memories. And by the way I see computing, computing is about storing information as well as processing information. It's not just processor, it's also storing. So that's why you see two aspects, superconducting logic and memory in my talk. And after that, I'm more excited to talk about some future directions that the superconducting electronics is taking and the computing itself is taking. And so let's wait for that section to come. And finally, I'll conclude. So again, I have a growing research group at the University of Tennessee. Before I begin, I would like to thank them all because all of the slides that I'll be presenting are either made or contributed to by my students. So I have several students. This is not updated. I should add a few more names and photos. My research group is called Nanoelectronic Devices and Integrated Circuits Lab, or in brief, Nordic Lab. And here is what we do. We look at emerging and exploratory materials. Just a second. Can you see my laser pointer? Just checking.
Yes.
Okay, sounds good. All right. So here's what we do in our research group. We look at emerging materials, and that includes superconductors, obviously. And there are several other emerging materials that we have worked with in the past. And we try to find ways to use them in electronic applications, in a system level applications. Obviously, you cannot take a jump from materials to system right away. You have to go through the hierarchy of devices and circuits. And we belong here. We belong at the interface of device circuit. Basically, we work on device circuit co-design per se. We use emerging materials, often make models for them and explore interesting device ideas and see how we could make use of those emerging devices into novel circuits. And we do a lot of simulation and modeling, ranging from atomistic simulation to circuit simulation. And in terms of modeling, we do physics-based to machine learning powered data-driven modeling. So that's kind of like the core area of emphasis for our group, but we also do some characterization, tape out, like experiments as well. Here's again, I'm just doing it very quickly because I want to get into the actual topic of the talk. So just to very briefly give you an overview of what we do in our group, this is the entire, basically all research directions that our group takes. We look at interesting compact modeling approaches for emerging materials. And on this slide, this section of the slide, you see several superconducting devices, including Josephson junction and superconducting memory stir, but we also make models for other emerging materials. And then we are heavily interested in the memory and peripheral design because I love memories. Storing information is one of the things that I'm fascinated by. And when it comes to memories, we all work with room temperature ones and as well as cryogenic ones. And cryogenic electronics has its own place because this is basically over the last several years has been my personal favorite. But in addition to conventional cryogenic electronics, we are also looking at room temperature and analog electronics. So apparently, when you're looking at emerging materials, you find applications in many directions, analog domain, digital domain, storage, or processing information. So that's why you see like a broad range of things in our portfolio. So yeah, it is how it looks like. Now, without further ado, let's move ahead and get started with the actual presentation with some background and motivation. So on this slide, I wanted to highlight three transformative technologies of our time. And you must be hearing a lot about quantum computers, and space competitions are heating up again. High performance computing, I mean, obviously, it means different things to different people, but it includes supercomputers, but also includes the AI systems and data centers. And if anything, AI is exploding everywhere, right? So high performance computing is becoming more and more relevant and important in our daily life. Turns out These three transformative technologies that are seemingly unrelated are or can be connected by one common thread, that is cryogenic electronics. And I'll try to give you some examples of exactly how that is the case. Just to put things into proper perspective, when I say cryogenic, it means two things to two different group of people. Some people call 77 Kelvin, which is the liquid nitrogen temperature, cryogenic, at least in our field. But when I say cryogenic, I typically mean deep cryogenic because this is related to superconductivity. So I'm typically looking at liquid helium temperature. All right, so turns out these three different technology paradigms, which are seemingly unrelated, have three distinct problems that they're dealing with, and people are trying to solve these issues. For quantum, it's scalability. How can you have more and more qubits feed into a quantum computer, because that's what will make them useful. For high performance computing, it's extreme energy demand, which we'll talk about in a second. And for space electronics, how do you fit everything given the area constraint? Because once you basically send something out, you cannot repair, you cannot replenish or do stuffs with it. All right, so that brings us to the specific applications of cryogenic electronics, having ideas about the three major pain points. Can cryogenic electronics somehow help in solving or alleviating those pain points? So let's start with high performance computing first, because that's more obvious. AI systems require a lot of energy. I mean, I don't know if you're hearing about the unreasonable numbers that AI systems like ChatGPT or other large language models are taking up. There was a very recent article on New York Times that talked about how AI could soon require more electricity than some in some countries, including the Netherlands, Argentina, for example. So just imagine like a AI system in hardware taking up more energy than a country requires in an entire year. That's unreasonable to some degree. And these things are only going to get worse. This is taken from a Nature paper published in 2018, so it's pretty old by now. But it already shows an exponential increase in the energy demand for data centers, the green one, as you see. So the trends are alarming. So we have to do something to fundamentally change the way we design or develop high performance computing cores. Now, one option could be to go for superconducting electronics, because inherently it's known for several decades that superconducting electronics can allow for much lower energy switching with much higher speed. So low power and low delay compared to CMOS, and it could be many orders of magnitude depending on which technology you are using. But in addition to ultra high speed and high energy efficiency, there are some other advantages as well. And I think the biggest advantage would be lossless interconnect, because turns out in a large scale computing platform like supercomputers or other HPC, interconnects take up a significant amount of energy share, and basically you're wasting it. You're incurring resistive drop, and it's not just wasting energy; it's also hampering or hurting the reliability of the overall hardware. So we have to keep that in mind. If you somehow manage to switch over to superconducting cores, then you can also use superconducting interconnects that will save a lot of energy. Now, moving to the next concept, quantum computing. Here is how cryogenic electronics is useful there. And by the way, this is a slide to introduce quantum computer, but I'm assuming by now we all know that they're here, they're hopefully going to change the world, and they have advantages over the conventional computing paradigm. So you cannot just replace a quantum computer with a more powerful supercomputer. Okay. All right, so I'm skipping the motivation part for quantum computing itself, but assuming that we all understand quantum computers are useful and necessary, here is what a quantum computer is made of. It's a very simplified view. It requires three major sections. One is the quantum substrate itself, the qubits that we mostly talk about. We talk about qubits, but there are other things. Turns out you need a control processor to control these qubits, to program these qubits, to read out these qubits. That's just as useful as or necessary as the other aspect of the quantum computing system. And you also need a memory. I have a slide that talks about the need for memory there. Now, here is how, this is again a very simplified architecture for quantum computing. On your left, you're looking at what we currently have. You have qubits sitting in at extremely cold temperature, and I'm assuming superconducting qubits here. That's sitting in at 20 millikelvin or so. And then you have control processor that's controlling the qubits with basically lossy interconnects. And that's sitting in at 300 Kelvin. So there is a huge thermal gradient over there, and that leads to thermal leakage and noise. And it becomes extremely challenging to integrate more than a certain number of qubits, say several hundreds of qubits, because that brings in a extremely high amount of noise through the interconnects. Now, if we are to do anything useful, and by the way, before I move to the next option, when I said control processor, that also includes the memory, by the way. So you need a memory and a processor together, and both of them are sitting in at 300 Kelvin room temperature. Now, this is possibility one, which some people are considering right now. Can we bring it down a little bit to a little bit colder temperature, like 77 Kelvin, because liquid nitrogen is cheaper and can easily be handled, and then reduce that thermal gradient to some degree and allow for some few more qubits, few hundred more qubits. That's the possibility, but that's not the possibility. That's just a intermediate possibility. What is going to be the most useful one is this one, the second possibility, where we bring everything, the control processor and memory, below 4 Kelvin possibly, so that we can use superconductivity, not just because of the processors and memories that will become better, hopefully, but also for the fact that you can now use superconducting interconnects that will be lossless, and hopefully you have much less noise to worry about to begin with, and that could potentially lead to several thousands of qubits. That's the vision, and that's one of the big push towards using cryogenic electronics for quantum computing systems. Again, this is just like a zoomed in version of what I already talked about, but just gonna fast forward through it. All right, now just to talk about why memory is necessary. And by the way, when I say memory, even in quantum computing system, you need classical conventional memory. Why? These are just two examples there. For in all quantum algorithms, you need a large number of arbitrary rotations, and they require a large program memory. And also to maintain data integrity of qubit states, you need to do error correction, and that also requires large data of memory. So for both considerations, you need high capacity memory. And as you have just seen in the previous slide, that bringing them down to cryogenic temperature makes sense. So we simply cannot just use any memory at room temperature at a higher integration density. Now, we'll get back to this. We'll get back to the unique challenges of the existing logic and memory in a few minutes, but let's talk about the space related application as well. So space is more like a natural playing ground for cryogenics, as you can see, because deep space temperature is 2.7 Kelvin. So it's kind of like you are right at home there. Superconducting devices, using superconducting devices in spacecraft has several, benefits, as you know, and they are being used in several spacecraft, so it's not new there. In fact, if there was any application before quantum or HPC, it was possibly just space or aerospace applications. So there is no new motivations required there. One thing to keep in mind is that when you are designing superconducting electronics or other cryogenic electronics for space, you are limited by area, which is a major problem for superconducting circuits, and I'll talk about that here. So that brings me to the next set of slides where I talk about superconducting logic specifically, and I promise that I'll move over to memory after this. And again, we'll focus on some of our recent work as well, but let's take a look at the history. Let's take a look at what else have been done over years. So this slide shows you that superconducting logic design, this is specifically for superconducting logic, not superconducting electronics, because that dates back even before 1970, say. So superconducting logic has been here for decades, and people have been trying to come up with new ways to make logic circuits out of superconductors. And obviously, we are not there yet because there are some significant challenges that are very difficult to overcome. I'll talk about a couple of them. Just so you see, this is one of the recent ones, except for the ones that we are working on right now. So I wanted to just also show you what that means, because that's the most latest demonstration of a superconducting architecture in a microprocessor, and that was featured in IEEE Spectrum like very recently. So it's very interesting. This is from a Japanese group, and I think this is very interesting work. But obviously, like all the other works that were done in the past, has some limitations, and superconducting electronics in general struggling with several limitations, which I will talk about in a second. But when I say superconducting electronics, I have 4 different avenues in my mind for our group's activity. Logic and memory, which I will talk about today, but there is also 2 other avenues that we have looked at in the past. Oscillator design with superconductors, because obviously you have extremely high speed. Can you use that extremely high speed of superconductors to make powerful oscillators for certain applications? And also, I'll briefly talk about this application in relation to neuromorphic computing, which will probably be the very last slide of today's talk. Now, getting back to the actual discussion, here are some of the existing challenges that are critical for superconducting logic design per se. Most of the superconducting logic families, they are basically using inductors, and inductors have issues because they are bulky components. And oftentimes when you have inductors on a chip, there is concerns about cross-linkage and uh, interference with the neighboring entities, and to avoid that you have to space them out from each other, which is even counterproductive in terms of area efficiency, right? So you're trying to save a component from the other and you're spacing them out, and meanwhile you're wasting a lot of chip area. So that has been, I think, the most fundamental problem for superconducting electronics, because you need inductance to deal with many of them. And the other thing is superconductors have zero resistance when they're behaving as superconductors. So it's very difficult to do anything with voltages to superconductors. So voltage control, I mean, people have been trying to establish voltage control to superconductivity for a while now, but there hasn't been one really compelling way of doing so in electronics as of yet. So that's the challenge. The problem with current-based logic is that it's very difficult to branch out. And logic requires branching out because you need to drive one logic circuit with another and another. This is called cascading. For any processor architecture, you need to do a lot of deep cascading, basically several hundreds of logic gates driving each other, or even possibly more, depending on the complexity of the architecture. So if you cannot branch out, that's the challenge. Yes, we do branch out in current-based control, obviously, but you have to design specialized circuitry to help you fan out. And that special circuit will take, obviously, additional area, which is basically useless as far as computing goes. Now, with that notion in mind, in this field, we have been trying to address these challenges because in the past, and also in parallel to this, we work on conventional CMOS-based logic design. So we know what it takes to design a good logic. And when it comes to good logic, I think CMOS is the king. So basically, learn from CMOS and see what CMOS gives you, and try to bring some of them to a superconducting platform to avoid some of the issues that we're dealing with. And I'll talk about that in the next slide, but this particular slide is where I begin, because this is again a current-based superconducting logic. So obviously you are staying with the flow. We haven't moved over to voltage-based yet for this one. So this was done in collaboration with NIST, National Institute of Standard and Technology in the US. So basically this is based on heater cryotron devices. This is a cartoon of the device which illustrates how it behaves. So you have a gate terminal, you have a channel, superconducting channel. If you flow current through the gate terminal, given that the gate is resistive, it will generate heat through Joule heating, and that heat can be transferred over through an insulator to the superconducting channel. And if you exceed the critical temperature of the superconductor in the channel, then it will turn resistive. And then when there is no gate current, it will be superconducting. So basically, this is like a switch which could be turned on or off using a gate current. So it's like a current control switch, similar to a transistor. And this is not a new device. It's been here for a while, but we use this device in a completely new way to design a logic family. This simplified version that you see. This is a symbol of this device. We used current biases in a way to achieve all fundamental Boolean logic. So basically, you are dealing with different current inputs and using the same topology. So this is not just one circuit. This is not AND gate. This is not OR gate. This is basically all of these gates, because this simple circuit can be modified using or changing the bias currents that you see to incorporate all of these fundamental logic gates. And what that gives you is, what we call camouflaged logic design. And here's what I mean by that. Before I move over to this one, let's compare that to a CMOS logic. This is a CMOS inverter, CMOS NAND gate, CMOS NOR gate, and this is how their physical designs look like in actual hardware. And you can, if you see closely, you can easily understand that there is a difference in the actual design. And somebody could reverse engineer just simply by looking at the physical design of this logic and understand what type of circuits are being incorporated. That raises concerns with reverse engineering, hardware security issues, and stuff like that. So if you could design circuits that look exactly the same, no matter what the gate is, that would be considered as a camouflage logic design. And now let's go back to this reconfigurable logic. Oh, by the way, this is also reconfigurable because the same circuit can be reconfigured to incorporate different type of Boolean logic gates. So keeping that in mind, take a look at this simple, toy chain where you have 4 samples of the same logic. Turns out they are actually incorporating different logic functions, and I don't have that written here. One of them is an AND gate, the other one is OR gate and NOR gate. So together they incorporate a specific Boolean logic. If you see this section in green, this is a Boolean logic incorporated by this circuit, and the green ones that you see, they represent that if you provide this much current, this will lead to a logic output equivalent to this Boolean function. On the other hand, if you see the red currents, and if you provide the red marked currents to the same circuit hardware, you'll end up with an output which is equivalent to this Boolean function. Okay, so that shows that this simple block is reconfigurable simply based on the biasing current level, which is possibly giving you a perfect camouflaging effect, because you cannot easily understand without looking at the circuit in action what this circuit is going to implement. All right, so that's the problem is it's still a current-based superconducting logic. So we are not losing anything new there, but we are not gaining anything either, apart from the fact that this is camouflaged and this is reconfigurable, which is also a big plus. Now, moving to the next one, this is where things start becoming more interesting to me, because we try to look at voltage-based superconducting logic. So this was a device recently discovered and reported by another group, not by us, obviously. So we looked at their work, and this is more like a physics or material science work, and we looked at their argument about how ferroelectricity can affect superconductivity. So basically, when you have a squid, which is one of the most popular superconducting devices ever, and when you fabricate a squid on top of ferroelectric material and program the ferroelectric material to be in positive or negative polarization, like you see here, depending on the type of polarization in the ferroelectric layer, the critical currents in the Josephson junctions of the squid will be different, because there will be interaction between the surface charge at the ferroelectric and the Cooper pairs through the Josephson junctions, and I'm not going into the details. And by the way, if you see a common theme here, I'm not getting into the really nitty-gritty details of any of these technologies because I'm trying to keep it fairly at a higher level. But I'll be more than happy to answer questions during Q&A or even beyond. You have my email, so I'll be more than happy to do so. My idea is to give you a sense of the overall landscape of the field and how it is growing without focusing on one key technology. So again, getting back to the point again, phenomenologically speaking, without getting into the real reason of why that happens, the polarization in the ferroelectric material, whether it's positive or negative, will lead to 2 different levels of critical currents in the squid structure. And using this phenomena, we proposed a logic topology that achieves all the fundamental elemental logic gates, like copy, NOT, AND, and OR. You might be wondering by now, why are these guys just designing logic gates and not a processor? And by the way, we are basically heading towards designing a processor, obviously, but in Boolean algebra, if you could incorporate these fundamental logic gates, that represents that you could incorporate any random logic, because they are the building blocks, like Lego blocks for large-scale logic. Okay? So that's why when we think of a new logic paradigm, we always test at least these logic gates and obviously possibly beyond to make sure that we have a generalizable logic approach. Now, you see one additional device here. This is a symbol for a ferroelectric squid. This 2 represent the squid. This represents the input at the ferroelectric terminal. But there is another device that's connected to the ferroelectric squid. Why is that? So as I told you that we try to learn from CMOS logic and bring the features to the superconducting paradigm. CMOS logic has 2 big advantages. One of them is obviously voltage-based control, which we are trying to achieve here, input voltage, output voltage. So if you have current-based control, branching out is an issue. The second one is rail-to-rail swing, meaning the range of your input. For example, if your input is from 0 to 5 volt, your output should also be within 0 and 5 volt. And there are several works and several papers in literature where people try to propose logic, and you see inputs from 0 to 10, output from 2 to 3. So for example, I'm just making up these numbers here. Okay, so that represents that you don't have a logic platform that is cascadable, meaning you cannot drive one logic gate with the other, because the output of one logic gate will not be enough to drive the next one, or will be too much to drive the next one. So CMOS has rail-to-rail swing, meaning the input and output voltage levels are within the same numbers. And that's exactly what we tried to achieve. And we couldn't achieve that without having help from this extra device called heterocraton, which I just talked about in the previous slide. So merging the collective interactions between these two devices, ferroelectric squid and heterocraton, we designed this 4 fundamental logic topology. And by the way, you see for AND gate, we use a parallel combination of FP squid. For OR gate, we use a series combination. And together, and again, I'm not going into the exact detail of how they do it, and these are all available in our papers, or I can answer questions. But I want to show that using these fundamental logic topologies, you can now design more complicated logic. So this is more complicated logic that uses all of these fundamental gates, like NOT gate, AND gate, OR gate. And take a notice to something interesting. You don't need any intermediate blocks to help it branch out. Basically, since this is voltage based, it can branch out theoretically to indefinite number of branches. Obviously, practically there will be some limits, but theoretically it can branch out to several different branches. So it's similar to a CMOS. The other advantage of this being similar to CMOS is that, so this is a representation of a logic circuit. You could just replace this with CMOS circuits, or you could replace it with our superconducting circuit. So apparently this is perfectly symmetric or analogous to CMOS based Boolean logic design. That gives you a tremendous advantage because CMOS is mature and you have a lot of design automation tools. If you could basically replace the individual logic gates with superconducting logic gates like this, you could then use the power of years of work, decades of work on electronic design automation, and then design large scale like RISC-V processor kind of thing with superconducting. Obviously, just to check and benchmark and make sure the numbers look right or numbers look promising. So that is a very big advantage to making them similar to CMOS. Okay, all right, I'm going to move over to the next concept, and I know that that was very superficial, but that's deliberate. So moving to the next one, superconducting memory particularly, and this is again the hierarchy of superconducting memory. They have been here for decades, and many of the work were actually limited to very small scale memory devices like 4 kilobit or so, which is not really practical or useful for applications like quantum computing and others. To be honest, anything at this stage of electronics. So we need much more integration density from superconductivity. You might be wondering what limited the integration density, right? Well, I mean, one of the things that I blame is inductor. Memory, if anything, memory needs to be even more dense than logic because you need to arrange memory devices in an array in rows and columns. So they will be much closer to each other than possibly a logic block. So that raises questions about can we still use inductive coupling and things like that. So we have to think out of the box and come up with some new approaches. And that's what we are hoping to do. So this is a device that we came across, proposed by groups of scientists from University of California. They theoretically proposed this device, which is obviously dubbed as superconducting memristor, but this is essentially a conductance asymmetric squid with 2 Josephson junctions that are asymmetric. There is a specific ask. Their critical currents need to be closely matched with different levels of conductance. So keeping that in mind, basically, in a simple word, you need to have Josephson junctions made of 2 different types of superconductors. And turns out, theoretically, that can lead to a current voltage property that has hysteresis in it. And if you extract the resistance out of it, you see that for certain voltages, you can experience different levels of resistance, depends on how you program this device. So for example, if you program it with a high voltage, it can transfer from high resistance state to low resistance state. And once it goes there, you see even at 0 voltage, you have 2 different resistance levels. That means once you program this device into a specific resistance level, it will remain there. Next time you start it again, it will start from that resistance level, and it will remember that I was programmed to the other resistance level. All right, so that's called non-volatility. Even when you shut off the voltage, it will remember its previous states and start from there. So this is basically a ready-made memory. We use conventional memristors to design memories, and this is like a superconducting version of conventional memristors, which you could easily use, in a memory design. And by the way, this is a deja vu of the previous discussion of heterocraton. I just wanted to put that here again because we need help from both devices. This is the symbol of superconducting memristor. This is a symbol for heterocraton, and using them together, we design a memory array. And let me introduce the unique challenges of memory array. When you're trying to design a memory device, oftentimes we see that people take a device and they measure it, they program it, and they sense what is stored, and they say, oh, it's a memory. The problem with that approach is memory is not sensing or programming individual device. It's about programming or sensing them in an array level scenario, because memory needs address. That's how they are read or written, like in rows or columns. So when you put them in association with others, you are sharing resources like interconnects and drivers and sense amplifiers. How can you read or program one of the memory cells without disturbing the others in the same row or same column or neighbors? So that's the biggest task for memory design. And just to achieve individual read and write operation without disturbing others, we needed an extra device, for this case, heterocratron, and we needed this complicated architecture. This is, again, I'm skipping the details of the architecture, but these lines show you the travel path for current during programming and reading operation. Okay, so these are, these are simulations, by the way. We haven't implemented them in hardware. This is simulation results, but that shows how you can possibly read or write into these memories. Moving to the next one, the same device can be used to design a memory. And the idea is kind of simple here. You program or write information in a ferroelectric gate by changing its polarization, applying a voltage, but you read through the squid structure. So it turns out, since you have two critical current levels in the squid structure corresponding to different polarization, if you apply a bias current that is within the hysteresis here, depending on whatever polarization was stored, you either get superconducting response from the squid or resistive response from the squid. So sensing this response from the squid, is it a superconductor or is it a resistor? Just by sensing that, you could make, you could understand whatever was stored in the ferroelectric gate, and you could read the memory that way. So that's how you read, using a different channel, and you write into a different channel. So that's separate read-write path, which is a very big advantage for memory design. And this is, again, a simplified abstraction that we love using because that makes it similar to other memories. This is ferroelectric squid. This is heterocratron as an access device. Remember, we use heterocratron to just control a particular cell selectively without hampering the others. That's why this access device is being used. But the memory read and write operations are all occurring at the ferroelectric squid structure. Obviously, you have to design that in a different way. As you see, it looks different, it works in a different way. So the unique approach, unique opportunities and challenges of the devices need to be kept in mind while designing these arrays. For the interest of time, I'm actually fast forwarding, but again, please feel free to ask me questions. I know that I'm not giving you too much detail here, but good thing is all of these are published work. So if you're interested in any of them, feel free to just look up our paper and reach out to us, and we'll be more than happy to talk about this. Now, I'm more excited to talk about some future opportunities, because logic and memory, okay, they have been here for a while. People are working on it for decades now. But what's new is the concept of computing memory, or relatively new, I should say, computing memory. People realized several years ago that the architecture that we're currently using, which is called von Neumann architecture, which served us well for decades actually, so very impactful architecture, where we have different processor physically separate from a memory block, and you have to communicate between these two blocks, fetch information from the memory, process, and then put that back into the memory after you're done processing. And that communication, that data exchange, take a lot of time and obviously energy. And that has now become a challenge given the huge workload for AI systems and other high performance computing systems. So if you spend a lot of energy and time just bringing data and putting the data back, it's not going to do us any good. So people have been thinking of, can we go for an alternate architecture called computing memory architecture, where you could potentially compute within the memory array. So basically, you don't have to compute everything, but whatever is being repeated over and over again, some simple compute steps can be brought into the memory array itself, and that thereby you could save a lot of area, especially in tasks like AI. Turns out AI-related tasks are often repetitive and simple, like, for example, a dot product engine or matrix vector multiplication. So this is MVM, stands for matrix vector multiplication. All you do is basically multiply two vectors, as you see. So very simple computational step, but you do it over and over again billions of times. And every time you need to fetch information from memory, process it, and put it back. So this is insane if you do it in a conventional architecture. So that's why this is in a high-level scenario. Remember that ferroelectric squid-based memory that we talked about? Turns out it is not just a memory for the sake of a memory, because you can use other memories. But it is a memory because it also gives you a unique opportunity to do some computation within the memory itself. So we figured out and we proposed a way to map one of these vectors in one of the devices and the other one in terms of bias current. And merging these two, to compute within the memory array this matrix vector multiplication. And by the way, just to show you how powerful that is, you within the memory array that is storing information, you could use the memory array to detect, for example, digits or any other thing. This is a very simple exercise that people always do in their papers to show, okay, you can recognize digits using. And by the way, these papers are published by now. This was published in DAC. Sorry, I mean I should have updated this, but it's also available on archive. All right, so logic in memory or compute in memory at cryogenic paradigm is extremely useful. It's not just, oh, okay, this is a fancy new thing. It's actually critical given the unreasonable amount of workload that AI requires. So at least for AI systems, if for nothing else, we need compute in memory, even in cryogenic temperature. You might be wondering, okay, at cryogenic temperature, we have like much less energy demand. Okay, so do we still need that? And we have very fast devices. Sure. The problem is at cryogenic, you're also limited by the thermal budget, right? So if you do a lot of data exchange, is going to increase the temperature and you'll have a lot of coolant cost. So doing compute in memory will solve the problem with additional coolant cost there. Moving to the next concept, I want to at least cover these concepts before we stop, because I think these are very exciting, and I want you guys to go and look it up and hopefully consider some of these as future directions. So cryogenic neuromorphic hardware is another new paradigm that we are also interested in, and many other people are working on it right now. I mean, I know that it may not be obvious to the community why neuromorphic computing is useful. Neuromorphic computing is the science of learning from the brain and possibly designing computing hardware that behaves or works in a similar fashion as the brain. They're not trying to make a brain. Obviously, that's not possible given the technology that we have right now. But we can always get inspiration from the brain and make our computing hardware more like the brain. Our brain doesn't have Boolean logic gates or memory block that communicate with each other. It's a very different working principle. But the good thing about our human brain is it is extremely energy efficient. Extremely, it's unbelievable how energy efficient our human brain is. So we could solve a lot of issues with conventional AI-based energy demands if we could somehow have some of this inspiration put into our AI hardware system. And that's what led to neuromorphic hardware design, which learns from the human brain, tries to make mimics of artificial neurons, mimics of neurons and synapses like the brain, and then connect them in a way that's in a neural network. So rather than having a software-based neural network, you have a hardware-based real neural network where you have neurons, you have synapses, and basically you make them compute like the human brain. Maybe you don't need to learn how to like sing or whatever, but you can learn how to detect something. So you have targeted tasks that you assign to this neuromorphic hardware, which they can do in a very energy efficient way. And they're being used for applications like, say, event-driven camera, which, for example, needs to be energy efficient, among other things. So what is the big problem in the neuromorphic domain? And this domain has been here for like a while, like more than 2 decades now. The problem is, these numbers tell you, Intel and IBM, they're one of the leading industries that are working in neuromorphic computing, and they're trying to make hardware and processors that are neuromorphic processors. Intel recently made Loihi 1 and Loihi 2, which are their flagship neuromorphic processor. I want to show you the numbers here. Loihi 2 only has 1 million neurons, okay? But our human brain has 86 billion neurons. So basically, even with this advanced technologies and manufacturing, we're nowhere close to the complexity of human brain. Why is that? One of the reasons is we are using superconducting, sorry, not superconducting, we are using semiconducting electronics, and that has lossy interconnects. And when you try to make big arrays of synapses, you deal with voltage drops and resistive drop, which limits the scalability of these arrays. So you have to break them down or keep them limited. One possible approach to try to approach the complexity of human brain and have a humongous amount of synapse and neurons in a system would be to go for a superconducting platform that could allow you to use superconducting interconnect. Obviously, then you have seemingly unlimited, or not practically unlimited, theoretically unlimited size of array, or at least much bigger arrays than the semiconducting counterparts can provide. So this is one of the motivation, not only motivation, there are many other advantages. So keeping that in mind, people have been looking at architectures like this, designing neurons with superconductors, designing synapses with superconductors, and then merging them together to create a superconducting neuromorphic platform. And inspired by this is not our work, by the way. Inspired by this is taken from a review article. I really like the animation. So inspired by this architecture, we started designing artificial neurons with superconductors and artificial synapses with superconductors. And these are some of our recent works, recently published works. This is an artificial spiking neuron based on superconducting devices, and we used several of them. This is superconducting nanowire. This is superconducting cryotron. Here, a superconducting cryotron, and then a superconducting memristor. So using the interesting interplay between these three devices, and there are reasons for all of them. And I mean, if I try to give a little bit more detail, these two are oscillators. So basically, that's how we started. We started looking at superconducting oscillators. Turns out, if you couple two superconducting oscillators, you can create a spiking neuron out of them. Obviously, there's a design approach, but it is possible to do so. And you use this heated cryotron to program. And what are we trying to program this special neuron has programmable spiking rate. So basically, you can increase the spiking rate or decrease the spiking rate. Again, I'm not going into the detail of it, but these show that you can have different type of spike rates. Fast spiking, slow spiking, depending on what is stored in the superconducting memristors. And this is a detail of how you do it, how you perform the spiking operation, how you do the programming operation. Obviously, I'm going to skip that, but it's possible. It's available in detail in our paper. But this is what you're achieving in addition to just making a neuron. These superconducting devices are allowing you to have extra features into the neurons that you could not have in a conventional semiconductor-based neuron otherwise. This is the last slide of its kind, superconducting synapses. Obviously, if you have neurons, you also need synapses to have a complete superconducting neuromorphic platform. So this is our own superconducting synapse design. Obviously, there are many other designs available in the field. And that uses, what is the advantage of this? It uses the exact same three devices that you saw in the neuron design, but in a very different organization and very different principle of operation. And it achieves different levels of resistance, which represents different weight of the synapse, by the way. So you can control the synaptic weight. You can program it using this superconducting memristor. And so moving forward, and by the way, this simple snippet shows you that using the previous neuron with this synapse, you can now make the vision of a neuromorphic platform with all superconducting devices. And this is something that I will end with. I just wanted to show that when it comes to zero resistance, superconductors are not the only device that gives you, or only platform that gives you zero resistance. Now, very recently, people are looking at twistronics and topological insulators. You can also make use of lossless conduction in some of these devices. And obviously, this is taken from a science paper which demonstrated a device called twisted bilayer graphene on hexagonal boron nitride, and it showed quantum anomalous Hall effect, which creates topologically protected Hall voltage levels like this, and it provides zero loss conduction through the edges of the device. Okay, so zero loss conduction like a superconductor without using a superconductor is possible. And some of these devices can be used to make cryogenic as well. So superconductors are not the only ones that need to be used for less than 4 Kelvin operation, but obviously they're more mature than some of these devices. I wanted to show, this is one of our previous work. We tried to use this device to make a cryogenic memory. And obviously, remember, if you have two physically identifiable stable states in a device, you could possibly use it as a memory, because one of those physically stable states can represent 1 and the other one can represent binary 0. And there you go. You have a representation for 1 and 0, and that's the memory. All you have to make sure that you can program them in a reliable way without hurting without hurting the nearby devices. And also you have to be able to sense them in an electrical way. So again, I'm not going into the detail of this, but I just wanted to show you that this particular device gives you 2 resistance levels, and it can be programmed with appropriate current, basically critical currents, like I said, superconductors, but not a superconductor. And then you have pretty much and this is also 4 Kelvin, as you see, measurement. This is the memory array that we designed with or proposed with this topological insulator device. This is a symbol of that device. So superconductors are not the only things that give you the advantage of zero loss conduction and things like that. All right, I'm not going to go through the detail of this. This is not related to superconductivity. I want to conclude, given the time. I just want to conclude with a very simple, punchline from Albert Einstein. So basically, we are trying to imagine. We are not trying to limit ourselves to the conventional ones. Maybe we'll make mistakes. Some of them will not work as well as we hope, but hopefully some will. So there is no bound to imagine things, and that's what we are trying to do. Because as Einstein said, a true sign of intelligence is not just knowledge, also imagination. So we are trying to imagine and do as much new things in the field as possible. Before concluding, I would like to acknowledge support and help from all of my collaborators. Without their help, none of this would have been possible. And then also funding support from our sponsors from Department of Energy, Defense, and National Science Foundation. And with that, I'd like to stop. Thank you all for listening in, and I'd like to take questions.